I'm demonstrating an Austrian Microsystems AS5040 magnetic rotary encoder, which detects the rotation of a magnet with a precision of about 1/3 of a degree. I've set up a test stand using Lego blocks that holds a magnet about 2 to 4 millimeters away from the IC. I designed a circuit board with 2 LEDs that visually indicate if the magnet is correctly positioned. If I move it outside of the range like this, the LEDs glow, so I know where in the system the magnets are supposed to be. Above the test stand, the oscilloscope is reading 2 of the output sets from the IC. On the uppermost trace right here, you can see a pulse width modulated output for driving analog detectors. As I change it, the width of the pulse changes. The lower 2 traces down here are quadrature outputs, allowing it to emulate a standard rotary or linear positioning encoder for driving servo amps. They're static until the chip detects a rotational change, at which point they show direction and speed of movement by their frequency and phase relationships to each other. So as I turn them, you can see if I turn quickly, the pulse train gets shorter. As I turn more slowly, the pulse train gets a lot slower. If I turn in the opposite direction, it's hard to tell this from what you're seeing, but they are reverse phase from when I'm turning in this direction. So behind the IC, there's an Arduino that's talking to the IC and clocking out positioning data via the serial output of the IC. The Arduino is sending this out via USB to the laptop over here on the right, where you can see the output data as it shows up in the terminal, right here. So as I turn it, you'll see the data change. I wrote an Arduino sketch that collects the data, turns it into a degree measurement, and also analyzes the status information that the chip's exporting to catch and display any errors that the IC detects in its output. So for instance, if I pull the magnet out of range, and back over here to where this guy is, and come out of range like that, you'll see that it'll start reporting magnet out of range. When I push the magnet back into range, it'll start correctly reading again and correctly tracking my changes in angle. This sketch happens to read the chip about once a second. The chip will happily run 10,000 times that speed if you need faster updates. I will be providing this Arduino sketch on our webpage at some point. I have to clean it up a little bit. The chip can also be set to output drive information for brushless motors and other configurations, and can be individually tuned to specific magnet IC configurations if you need to do that.